Good morning and good afternoon to everyone. This is Steve Case with Electrified, and looks like we're going to get started here right at the top of the hour. And welcome to our Fast and Furious series with Tektronix. We're focused on automotive today, and we'll be discussing scope tips for EV testing and serial bus decoding. And so let's get started. Today, we have our speakers, of course, from Tektronix, but they're all focused on the automotive segment. First up will be Dennis Solomon. He's the Automotive Market Segment Manager with Tektronix. Then we'll have Natalie Palmisano, our Product Application Engineer with Automotive Applications, and Yogesh Pai talking about power solutions, which, of course, are key to EV applications. Good morning, everyone.
Morning, Steve.
And before we get started, I'll just mention a couple of things. I'll be looking at the Q&A session. So if anyone has any questions, I'll be looking at those, and then each one of the speakers can ask if there's any questions, and we'll share them with the group. So that's convenient because we have 3 experts here today. That's excellent. But before we do that, I'm just going to have a brief discussion about Electrified and what we do. We're a large technology provider for test and measurement equipment and other technology equipment, but we're worldwide now. We're in North America, Europe, and Asia, with offices in mostly California for the test and measurement equipment, in London and in Europe and in Belgium, with both test and measurement equipment. And then we're also in India and in Malaysia. So we have offices all over there, and China also, sorry, covering test equipment needs wherever you're building, wherever you need the equipment. Electrified is there. We're also a distributor for Tektronix in North America, and have a lot of equipment on the shelf, and we're ready to present those. So with that all said, Dennis, I'm going to make you presenter so we can actually get started here. Here we go.
All right. Thanks, Steve. Good morning, good afternoon, folks in US, and good evening to anyone joining from all over the world. Thanks for taking the time, and thank you, ER, for having us here. I'm being joined by 2 of my very capable colleagues, Natalie and Yogesh, who will be helping us dive deeper into the automotive applications and use cases. Okay, I'm very excited to share some of our innovations at Tektronix, but I'm also deeply interested to learn what's top of mind for you attendees, your challenges, your needs, and any trends that you are seeing in your space. So please share questions anytime during the talk using the chat window, and we'll get back to you. So I want to kick the discussion off by looking at the inflection points in the mobility industry. Over 100+ years ago, we had our first inflection in mobility, and we had a Freedom machine that was born. It gave people lower transportation cost, more convenience, a better and faster traveling experience. With all the pluses, there were some trade-offs, particularly in terms of safety and environmental dimensions, which brings us back to this second inflection point in the transportation today. Today, we are looking at electric cars that are forcing automakers to rethink supply chains and also redefining what it means to be a car person. Looking at some industry stats, I see that there has been an increase in demand for software and electrical electronics engineer in this industry. In fact, a 15% increase there, and EVs, which are now accepted as the future for the transportation segment. It's an incredible change in just the 5 years we have seen this. EVs were perceived as a niche product, and the timelines were laid out far along, but now it's already here. And the shift from assisted to autonomous driving has a little longer time horizon as it requires changes to the framework, regulatory framework, as well as social acceptance and mitigating the risks around the test methodologies. So, but this is an interesting and a very active space we find ourselves in. The mobility industry is transforming right in front of our eyes, and Tektronix is playing a key partner, partnering with the automakers, tier 1s and tier 2 suppliers across the ecosystem to make this change possible. Let's look at some of the challenges that our customers are seeing, and given the paradigm shift in mobility with the case megatrends of connectivity, autonomy, electrification, and shared, we, from a test and measurement perspective, see a lot of opportunities to co-create with our end customers. 3 spaces that we have been actively engaged with our customers on are around vehicle electrification, so EVs, the connected cars, and the AVs. So around the vehicle electrification, there is an increasing need for power conversion efficiency. So there is a need for high voltage platforms, as well as a need to have efficient conversion of energy from the battery packs to the traction inverter motors. Here, there is a need for newer test power electronic designs based on wide bandgap materials such as silicon carbide and gallium nitride. And we'll talk about that here shortly, how we are unlocking the challenges that our customers are facing in this space. On the data and connected car space, communication is the key. So we have solutions that are catering to the signal separation needs of these networks, especially around Automotive Ethernet, which is becoming a dominant standard as we move forward in this evolution. And finally, we have the autonomous vehicles. So ADAS and autonomous driving, they present brand new challenges that that the industry is now coming to terms with. There are some very capable instruments that we provide to further the research and development in this space, all the way from our signal view software to our AWGs, which are arbitrary waveform generators, as well as to tackle the wide bandwidths, a broad range of spectrum analyzers. A quick snapshot before we dive into the specifics here. At a high level, these are the different market. This is our view of different market segments within the industry. Tech caters to all these segments and can help you address some of the unique test and measurement challenges across the ecosystem. So we work with tier 2 semiconductor customers, tier 1 customers, as well as automakers, OEMs. We'll be spending today's discussion most of our time around powertrain applications and in-vehicle networks, going from low speed all the way to high speed. Here's a quick snapshot of our automotive application areas. As I pointed out, again, for our discussion, we'll be focusing on EVs and IVN applications. Think of EVs as replacing the traditional internal combustion engine with an electrified powertrain, and think of IVN as the central nervous system, connecting the mesh of ECUs with the sensors and feeding the data back to the compute. With that, let me transition over to Natalie to kick things off in IVN, and followed by Yogesh for EV applications. Natalie, you have the floor.
Thank you, Dennis. Hi, everyone. Natalie here, and I am a product application engineer with a focus on automotive solution. And like Dennis said, I'll be talking about in-vehicle networks. So what is in-vehicle networks? It refers to an automotive data communication system that is used to connect electronic control units, or ECUs. And some examples include CAN, LIN, and FlexRay, which is what we'll talk about today. So many vehicle designs use CAN and LIN or FlexRay to communicate among ECUs. and between ECUs and sensors, actuators, and displays. These buses are critical in providing real-time communications in and throughout the systems, like the braking system or infotainment systems. CAN is the primary bus used for engine timing controls, anti-lock braking systems, and powertrain controls. LIN is a lower cost alternative to CAN bus, and it is primarily used in applications when communicating between sensors and actuators. And lastly, FlexRay is used in X-by-wire applications and is used like brake-by-wire or steer-by-wire. So with these serial buses, they are a more mature bus protocols and are designed to be robust and easy to integrate. But there are some challenges that can occur, like excessive bus errors and lockups. And with serial buses, a single signal often includes address, control, data, and clock information, and it makes it hard to isolate these events. So using an oscope that is equipped with protocol decoding, you can visually see the decoded bus traffic and signal quality, which makes it great for troubleshooting at a system level. So let's talk a little bit about how to decode. So some key features of our serial decode allows you to trigger on all critical elements of a serial bus. So that means that you can decode all the critical elements of each message, so you wouldn't need to count ones and zeros. You can search through long acquisitions with your criteria to find a specific message. And lastly, our event table shows decoded serial bus activity in a tabular timestamp format, so you can have a quick summary of the system. On the scopes, it's pretty easy to decode. You can press the front panel button and you can define the inputs to the scope as a bus. So for CAN and LIN, it's pretty similar parameters, and you would do the CAN standard or LIN standard type of signal, input signal, bit rate, voltage threshold, and sample rate. But for FlexRay, it's a little bit different, where you would need to specify the channel type, signal type, voltage thresholds, and bit rates. But when it comes to voltage thresholds, FlexRay requires 2 thresholds to be set to enable the oscilloscope to recognize data high and data low, as well as the idle state, where both signals are at the same voltage. Moving on to our next slide, we will show a short video on how to decode and trigger a CAN bus.
Hang on a second, we'll get your video ready.
Hi, my name is Austin Hall. I'm a Tektronix application engineer. Today I'm going to show you that setting up a CAN bus for decode, triggering, and analysis on the 5 Series MSO is extremely easy. With a valid signal on channel 1, press Default Setup, and then Auto Set to scale the waveform correctly on the screen. Tap Add New Bus to add a bus. Now you can select CAN from your bus type dropdown. This signal is a CAN high signal running at the 2.0 protocol. We can also do CAN FD, ISO, and non-ISO versions in our decode. We want to make sure that the bit rate is set correctly. 5 megabits per second is what this signal is running at, so we can leave this correct. Now we want to set a threshold. We want to select a signal that's between the top and the bottom of our signaling. 2.7 volts should be enough. Now we want to scale out the waveform so that we can see enough of the decode happening. Next, we're going to set up our trigger. Double tapping the trigger and then selecting bus from the trigger type will put us on the correct path. On trigger on, we're going to select identifier. Double tap the hex field and select an identifier to trigger on. I'm choosing 519. Now we'll zoom in so we can see our trigger point. Adding a results table and a search provide a wealth of information to the user. Stopping the acquisition allows us to move through both the results table with the multi-purpose knobs and the search with the navigate buttons independently. In just a few minutes, you can have your bus set up and start extracting useful information from your device.
And Natalie, I think we're back with your presentation. We're ready to go.
Great, thank you. So next we'll talk about Automotive Ethernet. So when it comes to NVL networks that require faster speeds than CAN, LIN, or FlexRay, this is where Automotive Ethernet comes into play. So today, vehicles are generating and transmitting vast amounts of data in order to implement advanced driver assistance systems, onboard diagnostics, cameras and sensors, infotainment systems, and smart safety systems. So typically, low-speed IVN is considered anything less than 10 megabits per second. So that includes 10 base, CAN, and LIN. High-speed IVN is anything greater than 10 megabits per second. And there are also two types of IVN standards. So that's symmetric and asymmetric. Symmetric is used for ECU to ECU communication and includes 100 base, 1000 base, and multi-gigabit. Asymmetric is used for items like the display or camera and includes multi-gigabit Ethernet, but the half-duplex version. So why would you use Automotive Ethernet? It's a cost-effective, lightweight option that can deliver data at higher speeds. It can transport data roughly 100 times faster than CAN bus. It can also operate in a rugged condition and wide temperature ranges. So the Automotive Ethernet cable are an unshielded single twisted pair designed for lower weight and cost, and PAM3 and 4 modulations to achieve high data rates and reliability. And of course, reliability is extremely important for systems that are designed to protect the safety of the passenger of the vehicle. So with Tektronix scopes, we are a great choice to test your Automotive Ethernet design and make sure you are within specifications, because we offer automated measurements like amplitude and time measurements, statistical analysis, and histogram to check signal qualities. We also have eye diagrams that would be the fastest and best way to evaluate complex PAM3 signaling for noise and signal integrity issues, and also jitter analysis tools to provide complete profiles of master and slave clock jitter. This also includes time interval error and cycle to cycle to isolate the potential source of errors. So with Automotive Ethernet, the master and slave device can communicate over the same link, meaning they are overlaid on each other. So the master knows what data is being sent and can determine the slave signal from the overlaid signal and vice versa. But it does make this hard to isolate the signal for signal integrity testing or protocol decode. So to solve this, there are currently two methods for separating master and slave signals. The first is the legacy method, which requires users to break or cut the Automotive Ethernet cable and insert a directional coupler to separate and test the signals, but there are a few drawbacks for this method. One is that it's not easy to cut the cable at the system level, so this method would not be used for system level testing. Next, it introduce insertion and return loss, making it difficult to determine if an error is a result of the system or a result of the additional hardware. And it also amplifies the noise in the systems and impacts measurements and characterization accuracy. The second method is the Tektronix's signal separation method that utilizes advanced software and probes to non-intrusively separate, which allows users to visualize the true signals with greater clarity. And this method addresses the drawbacks of the legacy method. So using the signal separation method, the signal quality is a cleaner eye diagram, and this provides an accurate representation of automotive Ethernet signals for signal quality measurements and the ability to identify potential performance issues faster. The next slide here, we have a longer video on how signal separation works, but we will not show that today. So I will hand it off to Yogesh to talk about powertrain.
Just want to point out, we will have the link to that video in the handout that we'll give everyone later. So it is available. We'll give you the link for that.
Hey, thanks, Natalie. Hi all, this is Yogesh Pai, Product Manager for Power Solutions here at Tektronix. So let's talk about the EV powertrain section now by first looking at a typical automotive test workflow. So the workflow is mainly classified into three blocks. On the left, you have the tier twos, which are mostly the semiconductor companies. And then we have the tier ones who are focused more on the systems, and OEMs who are the end automobile manufacturers. So mostly these are different companies, but in some cases, the same OEM company might be working on their own system designs and components. And if you see here, each of the segment has their own set of requirements and test plans, and therefore requires different solution to meet their needs. So let's look at them briefly in terms of key deliverables, test plans, and the end equipment used. So when it comes to tier twos, they are mostly focused on the design validation. So some of the deliverables here include the power management ICs, the reference designs, different types of components and boards, and their test plan involves measuring the power efficiency, power integrity, and working on the power management piece. And the primary test equipment that gets used here are the oscilloscope probes, various power supplies, SMUs, and so on. At the system integration stage, we have our customers working on inverter designs, traction motor designs. And because the focus is on the system, they care more about the system efficiency, stress testing, and simulations. While we see that the customers are using power analyzers, they do use the oscilloscopes for debugging. And then at the OEM stage, the functionality and interoperability becomes very critical. And therefore, the test plan includes the start and stop motor profiling, on-road testing. A lot of emphasis is put on safety and hardware in loop and driver in loop kind of testing. So the typical test equipment here are around dedicated test systems. But whenever there are failures encountered, then these customers also use the oscilloscopes for failure analysis. So the key takeaway here is that regardless of where our customers are, when it comes to debugging, a scope-based solution is very important to all three segments to solve the design-related challenges. So here you see some of the key components that constitute the EV powertrain system. First, we have the battery packs, which act as energy storage devices. They can range from 400 volt to 800 volt architecture, depending on the type of the vehicle. Then we have the OBC block, the onboard charger. They are used in cars which require the AC chargers to convert the AC to DC before charging the batteries. Then we have a range of DC to DC converters. As you know, there are different ECUs which operate at different voltage levels, ranging from 12 volts to 48 volts. it's necessary to convert the high voltage levels using buck converters to ensure that a proper regulated DC power is supplied to various components. And lastly, we have the inverters and motors. They are at the heart of the EV powertrain system, which help to drive the vehicle forward. And we see most of the companies are trying to optimize this block to gain the highest efficiency per unit of charge. So let's look at some of these blocks in a bit detail now. Okay, so the table here lists some of the high-level test challenges and the typical tests that are performed when it comes to testing various components of the EV powertrain. So when it comes to battery testing, understanding the welding element becomes very critical. As you know, the incorrect weld can generate excessive heat and result in battery underperformance and failure. And also these battery packs are exposed to a wide range of environmental conditions and therefore need to be tested for performance. So some of the typical tests that are performed include cell tab welding, open circuit voltage, bus bar welding, temperature and environmental testing, and so on. Regarding the OBC block, it is critical to measure the optimized charge times. We also focus on reducing the EMI effects. There may be elements of magnetic losses which need to be minimized, and most importantly, we also need to understand the isolation schemes between the high voltage and low voltage circuits. And some of the typical tests that are performed in this block include the power management, power factor correction, ripple, energy, various switching losses, EMI, and magnetics. Next, we have the DC-DC converters, where the critical test challenge is mostly around high temperature operation, efficiency, safety, and more recently, we've seen use cases of bidirectional power transfer. And some of the tests that are performed here include the power management, various power rail tests, power conversion losses, and bidirectional source sink tests and ripple. Lastly, we have the inverters and motor drive blocks, where the focus is on understanding the drivetrain system level complexity. There might be different kinds of motor variants, integration of e-motors, and understanding the system performance over long test times. The key measurements performed here include understanding the power quality of the system, efficiency, ripple, harmonics, field-oriented control, and understanding the motor start and stop profiling. So let's look at what Tektronix has to offer in terms of battery test space. Uh, Here are some of the key benefits of using our Keithley test solution for battery testing. As you know, there are several pain points associated with battery testing. There might be errors encountered during testing, which can involve a lot of manual test times and can impact the time to market. So leveraging on automating the test setup using the software Kickstart, or using custom scripts using TSP or test script processor can greatly help reduce errors. Then you know that the batteries operation when you're testing with them can be quite hazardous. So automated testing reduces the possibility of dangerous errors and humans coming in contact with the setup. The battery testing also in general uh, requires a lot of test equipment, so flexible solutions such as the 3706A DMMs can help you make some of these measurements using a single instrument. And data collection, analysis, and management is another time-consuming process. So a software like Kickstart can not only help you collect the data, but can also help you visualize this data. So we believe that the Keithley solutions are highly configurable for your voltage and current related measurements and can help address overall needs related to battery testing application. Okay, so let us now look at the various power converters, which includes the OBC block, which is essentially an AC to DC converter, and the various DC to DC buck converters in the EV system. The OBC block contains an input stage for EMI filter, which is followed by the power factor correction block, and that is followed by the DC to DC converter block. There are various protection circuits and power management blocks involved, and the communication can happen through various automotive serial standards like CAN, CAN-FT protocols. The OBC block should also maintain minimum EMI levels as per the EMI EMC standards. And just like the OBC block, the DC-DC converters can have the high power stage and low power stage and can involve transformers between them. The power levels can range from anywhere between say 60 watts to 180 kilowatt or even higher. And this can also have some bidirectional buck boost converter and can also leverage some of the automotive serial bus protocols for communication. The DC-DC converter blocks also include various losses and can lead to extremely high temperature levels ranging up to 300 degrees centigrade. And in order to maximize the efficiency, designers are trying to reduce the switching losses and dissipate the heat in a proper manner. And due to all these elements and high power involved, safety becomes an important parameter. To address the pain points of these OBC and DC-DC converters, Tektronix provides a complete solution that includes the 456 series MSO scopes, various voltage and current probes, and application software bundles. The automotive software bundle in particular offers the power and serial decode software options to meet the requirements of the design engineers. One can also leverage the spectral analysis capability on our scopes to measure the EMI effects and can debug some of these issues with ease. The power software in particular is of interest to our designers. It offers various measurements like power quality, harmonics, switching losses, and magnetics. And if you are testing the power converter configuration, particularly if that involves MOSFETs on the high side, you can also leverage the isolated probes for making those floating gate measurements, as isolated probes offer very high CMRR for making these kind of measurements. So with this, we believe that we have a good test coverage around the OBC and DC-DC converter designs. Now, let's look at the traction inverters block. The traction inverter makes up one of the main power electronics systems found in an EV, and it's used to control the motor to determine the driving behavior. The traction inverters convert the DC power from the onboard high voltage battery into AC power that is used to drive the main motor of the EV. In addition to this, the traction inverters also perform functions which are related to voltage boosting, switch protection, and regenerative braking. The inverter functions are controlled by an integrated PCB, which should be designed such that it minimizes the switching losses and maximizes efficiency. The inverter captures energy released through the regenerative braking and it's fed back to the battery. Therefore, the vehicle range is directly related to the inverter efficiency. Some of the key inverter related measurements that are performed during the design stages include the system efficiency, which is computed using the electrical signal inputs and measuring the output mechanical parameters. We also need to look for the three-phase output voltage and power analysis on the electrical side, and mechanical analysis, which can be done by probing some of the sensors on the device, like the Hall sensors and QEI sensors and so on. Harmonics also need to be measured, and typically we can measure up to the 200th order of harmonics, and which are tested for various IEC and IEEE standards. Control system optimization also needs to be done, and we employ the field-oriented control or FOC techniques. And understanding the dynamic load changes and system response over long records is also important to simulate the road test conditions. So we have enabled a dedicated inverters and motor drive test application on the 5 and 6 series MSOs. We call that option IMDA, that can be used along with the voltage and current probes connected to the device. This application supports various wiring configurations based on the designs. It includes key electrical and mechanical measurements, which we'll cover in the next few slides. And there is also an easy drag and drop UI available to make the debugging very smooth. We also support a global measurement configuration, which means if you add a single measurement and configure that measurement, all the other newly added measurements will inherit this configuration, making it very fast to get into the results with minimal user intervention. We also support application-specific graphical plots like phasor diagrams and harmonic plots, which gives the results visually to a user to debug easily. You can also easily document the results. You can save the results as a CSV file for offline analysis, or you can save the entire debug as a scope session file, which can be shared with across your teams. There's also a built-in demo session file, so you can recall this session file and make your changes instead of starting from the scratch. So it's very helpful in that operation. And we also support different types of sensor inputs. We supported Hall and QEI sensors, and with the most recent release, we also support resolvers. So let's briefly look at the IMDA electrical measurements now. So starting with the first measurement, which is power quality. This measurement gives complete insight into the three-phase electrical parameters. It displays the per phase power components and the total power of the measured signals. This measurement also supports on-scope phasor diagram, where you can look at the three-phase voltage and current signals, and you can get a complete understanding of how balanced the system is. Then we have the three-phase harmonics measurement. Harmonics can be a main cause of motor overheating. They can be measured by viewing the electrical supply to the motor input terminals in the frequency domain, and user can compare the harmonics measurement against various industry standards, or they can define their own custom limits. Next, we have the dynamic measurements, where users can gain insights into their system over long records and understand the dynamic behavior of the system across various load conditions. IMDA solution offers two unique trend plots on the power quality measurement that helps determine the dynamic performance. The first plot is the time trend plot. The second is the acquisition trend plot. Each plot has its own advantages. For example, you can use the time trend plot, which shows the measured value per cycle, while the acquisition trend plot shows the mean of the measured value per record over all the acquisitions. This allows you to capture long records of data to perform deep record analysis and understand the dynamic behaviors of the motor. These plots can also be saved as a CSV file for post-processing. Then we have the electrical efficiency measurement. So this efficiency is computed on the electrical side. So typically we can connect the DC input signal and three-phase AC output signal, which leverages all the 8 channels of the scope. Lastly, we have the DQ0, or direct quadrature zero, which supports the resultant vector. This is a key measurement when it comes to the motor control unit. And some of the interpretations of the DQ0 measurements are with the features like the resultant vector, filtering options, and navigation. It makes the process of analysis a lot more simpler compared to the conventional approach. The DQ0 DC component is computed and displayed as math vectors, and the data can be saved or post-processed. The DQ0 with rotor angle gives a good indication of the motor system efficiency. The results can be used to interpret the V reference from the space vector modulation, and the field weakening visualization is possible along with the phasor diagram by minimizing the D vector and looking at achieving higher speeds with the same flux. So a lot of this debugging can be done using this measurement. So you can see one can leverage various electrical measurements to debug their inverter designs. Along with the electrical measurements, IMDA also supports mechanical measurements as a separate option, IMDA-MECH. You can leverage the scope channels to probe for mechanical signals by using the logic probes, which conserves the number of analog channels. So each scope channel can be connected either using an analog probe, or you can use the digital probe, which provides 8 digital channels, which is sufficient for probing the sensors. Some of the key measurements include angle, speed, direction, torque, power, and system efficiency. We also support different types of sensors like Hall, QEI, and resolvers. So as you know, the inverter blocks conventionally are based on the silicon designs. And these days they are transitioning to wide bandgap devices like the silicon carbide MOSFETs or GaN FETs. And they offer increased efficiency. They have compact size, and they also produce lighter devices. We need to note that the test plans for wide bandgap are different than silicon and are based on newer standards that are being defined by standard bodies like JEDEC and IEC. And to meet this demand of the next generation designs, Tektronix has released a new wideband gap test application on the scope, which is released as option WBG DPT that provides automated measurements as per the standards. While the application currently provides 16 key measurements to the user, we have seen that the key challenge in testing is the high side MOSFET characteristics, as making floating gate measurements is quite challenging. And we can easily address this challenge by leveraging the automated software along with the isolated probes. Let's look at this new application in a bit more detail in the next slide. So here is the summary of the new wideband gap application, which significantly reduces the test time. It offers 16 standard specific measurements as two measurement groups. The first one is the switching and timing analysis, and the second one is the diode reverse recovery analysis. We've recently added a feature to perform the wideband gap specific DSKU operation. It also offers the signal conditioning and configuration options, as we understand that real world double pulse test waveforms are quite noisy in nature, and hence they need to be conditioned before analysis. There is also an ability to zoom the waveforms of interest, so you know exactly which region of the waveform is being analyzed. Lastly, there is a support for programmatic interface and instrumentation automation capabilities, so you can integrate this application as part of your test plan. So in summary, you can see that Tektronix offers a complete set of measurements that can help you perform design-related testing at different stages in your EV powertrain designs, from the input DC to output three-phase to traction motor and dynamic load analysis. We have everything covered as part of our solution offering. This also includes specific solution to help you transition to wide bandgap devices as part of your roadmap efforts. It's a little challenging to cover all the topics in a single webinar. So for more details on all the power solutions we talked about today, you can visit tech.com, where you'll find links to various application notes, videos, and data sheet. Feel free to contact your local Tektronix representative for more information, or if you want them to schedule a demo.
Thank you, Yogesh. I hope you got some value from today's discussion, team. I wanted to summarize what we covered today really quickly here. From a Tektronix perspective, we want to be your partner in your electric vehicle developments. We are a multinational company, and we provide you long-term support for your mission-critical instruments, preventing frequent qualification cycles, as well as the measurement confidence that you will get taking those measurements on our high-performance scopes, probes, and Keithley instruments. This will also help you minimize the time to market, as well as we touched upon earlier today, signal separation, a non-intrusive way to get those measurements, build your confidence in those measurements, as well as accelerate your time to market. We are offering straightforward automation and dedicated software, cloud-enabled software, so you can use tools like Texscope and Kickstart to easily pull together those frequently executed test workflows and automate them using PC automation software, as well as collaborate across the globe with your global teams over Texscope and TechDrive. Those are cloud-enabled as well. And most important of all, I think, is the precision and repeatability that you will get, that you can expect from Tektronix. So we offered some of the best probes in the space, and they are available to you. So thank you once again. We appreciate your time, and thank you for joining us. Back to you, Steve.
Thank you, Dennis. At this point in time, I'd just like to mention that we have put the copy of the slide deck and some reference links in the handout section of the webinar. And if anyone has any questions, now is a great time to go ahead and ask those. But yeah, Dennis, thanks to you, Natalie, and Yogesh for your team. It's really enlightening. It's a lot of information. Let's see if we have any questions coming. We don't have any questions so far, but if we do, I'll let everyone know. Amazing that we actually have, I'm just thinking about cars, and we actually have PAM3 and PAM4 level signaling going on in cars now. It's like years ago, you'd never think that this was even feasible, that have such high-speed communications in a vehicle with all the noise and challenges going on. Well, I don't see any questions, but thanks to you and your team, Dennis, and Natalie and Yogesh for the presentation. It was really awesome.
Thanks, Steve. And in the meantime, if you do get questions over email, feel free to share, and we'll be happy to get back to you.
Yep, we certainly will. Thanks everyone for coming to the webinar. We appreciate it. Thank you very much.